So hi everyone, and thank you for joining me for this talk. My name is Mathieu Tarral. I'm really excited to be here today at Hack.lu. And I have a short presentation today about how to debug a process from the hypervisor. So the agenda for today is that we are going to review what are the concrete benefits of having hypervisor level debuggers. Then we're going to quickly review the existing projects, and I'm going to explain why I decided to start my own implementation of this tool. But first, who am I? I'm currently a researcher at F-Secure. Well, I'm focusing on building sandboxes solutions, and mainly stealth sandboxes. So my main focus is on virtual machine introspection. VMI is, let's say, a way to analyze the content of a virtual machine from the outside, from the hypervisor level. And I did that especially on KVM. So the KVM VMI project is what I've started to as a, let's say, a common effort to bring an official VMI API on KVM. That's a bit of my background. So now let's start. Why hypervisor level debuggers are relevant? The first problem I can think of is malware analysis. It's because debuggers are noisy. A debugger will always modify, let's say, the execution environment of a debuggy. It's kind of this observer effect that you cannot avoid. And usually it's not a problem until you have to deal with a malware. But the core problem of that is that our debugging API, our operating system debugging API, have never been designed to deal with malwares in the first place. And we are still trying to analyze malware with that. So we are building workarounds and it's not really working. So we need to find more permanent solution to this problem. The second problem I can think of is that sometimes this observer effect is intentional. Sometimes you have some closed-source operating systems out there which are just trying to protect their features. If you enable the debugging on Windows, it will disable first patch guard and then disable the protected media path. The protected media path is a requirement to analyze, to let's say, start a protected environment to allow the execution of a DRM. So if you want to analyze DRM execution, you cannot use a debugger for that, because it's protected. And the final problem I can think of is that what you see here is the virtualization-based security model of Windows 10. You have the normal kernel separated from the secure kernel, and you have Hyper-V managing all of that. You can analyze and debug the normal kernel. There is an extension to debug the Hyper-V kernel, the Hyper-V, sorry. But there is, so far, not an easy way to debug the secure kernel. So we might need to find a solution for that also. So the solution I would like to use is to stop hacking around in the kernel and rebase our entire debugging platforms on the hypervisor itself to gain more privileges. First, what we will gain is stealth. The stealth we need to analyze malwares. First, because we are not using the operating system debug API, of course, so we don't leave any traces. And the second thing is that we can use invisible debug breakpoints thanks to EPT violations. And the second advantage is that we will have the full system analysis. The hypervisor has a full view of the system, of the guest state at any time. So you have the entire control. And on top of that, you can debug bootloaders because your debugger is available from the time your operating system is booting. But more than that, you have some benefits. Depending how you implement your hypervisor level debugger, you can have unmodified guest. You can use your raw virtual machine right away. So no serial cable, no specific hardware, and no specific guest configuration to enable the debugging. And plus, you have this on-the-fly debugging, so debugging a virtual machine without having to reboot it or change the configuration. And the last benefit I can think of is that what we can aim for is the cross-platform debugging infrastructure, where my hypervisor is able to debug the kernel of Windows, Linux, and macOS with the same tool. Think about it. We can have an OS-agnostic debugger, which, on top of which you are building your knowledge and your scripts. So it's quite convenient. So now let's review the existing projects that we have, and a bit the history. Are they used, are they maintained? I split this into two categories. The first one is bare metal debuggers. These kind of debuggers are being used to debug real hardware. So the first one I can think of is HyperDBG. HyperDBG, what they wanted to do is to see if it was possible to take the full control of a production system for forensic purposes. And how did they do that is by using a term called hyperjacking. Hyperjacking is that I'm going to take my host and virtualize it on the fly. So dynamically, I'm going to insert a hypervisor on the fly. So beforehand, they've been building a driver and installing it on the host. And this is virtualizing the host using the driver. So everything happens on the same machine. And if you press the key F12, you have this graphical user interface which is appearing, and which is the debugger itself. Now, the problem with that is that the hypervisor is writing directly to the video card frame buffer. So it's hardly maintainable. So let's move to the next project, VertDBG. VertDBG, what they wanted to do is to analyze patchguard, and patchguard specifically the obfuscation behind patchguard. So the same idea using hyperjacking, but this time it's a bit better because, well, they used a DMA attack to have a read and write access to the physical memory and inject their own driver into Windows. So it's a bit better because the guest doesn't know that's what's happening, and you don't have to install a driver beforehand. Everything happens dynamically, and the driver is injected into the guest. So it's better than HyperDBG in this way, and there's a DBD protocol because there is a client and a server. But we can do better. And first, DBG is doing better than that. What he wanted to do first was to have a better WinDBG UI. That was the main reason why he started this project. So he started reversing the WinDBG protocol, and at the same time, he realized he was also writing a hypervisor. So he said, okay, I can merge both of these projects in the same tool. That's what he did. And with ParsDBG, you have to, change your boot sequence, because the hypervisor is written inside an EFI module. So when you boot your operating system, you're going to boot on either a USB key or a TFTP server, which is going to provide you this EFI module. And then it's going to be able to virtualize any operating system behind that. So ParsDBG is better than the previous one because there's no driver. It's an EFI module. And then there is another category, which I would call virtual machine debuggers. On this category, we want to debug virtual hardware. And we take an existing hypervisor, and we are trying to build our debugging API inside it. The first project I can think of is Pyribox. Maybe you have heard of it. What I wanted to have is, let's say, a dynamic instrumentation system, high level, with a lot of callbacks. So they instrumented the whole QEMU as an emulator. They added plenty of callbacks inside it, and it's great, because you can have even callbacks on instruction level, or when a block starts and ends. And on top of that, you have high-level scripts in Python to introspect the guest. So it's really great for memory analysis, and it's maintained at the same time. And the second project I have is RVMI. So RVMI, what they wanted to do is to see why a malware sample didn't run in their sandbox and analyze it, understand it. So they took Recall as their main tool. Recall is a memory forensic framework for lack of volatility. And they added a debugger on top of it. And they instrumented the KVM hypervisor to add breakpoints inside it. So it's also maintained, and it's really a great tool. So that's a bit what we have in terms of hypervisor level debuggers project as of today. But now, where do we move from here? Should I use one of these projects or no? Well, what I want to do is malware analysis. That's my first goal. The problem is that I don't want to use Pyribox because it's emulation-based, and I would like to keep the speed of hardware virtualization. And I'm really interested in RVMI. It looks really great, and I'm going to. I have, let's say, some issue with the design of RVMI. I would like to improve it. So I will keep RVMI as a focus and improve it. What you are seeing is, let's say, a schematic version of the design of RVMI. We take Recall as the main tool, and then we are going to add a debugger on top of it, which is communicating with QEMU KVM. On top of this, what I would like to do is to first add a VMI introspection layer. I would like to add a hypervisor VMI layer. So I don't want to be tied to one specific hypervisor, but be hypervisor independent. And the second modification is that I would like to take a good reverse engineering tool or debugger as my main tool and add a small introspection layer on top of it. The goal is to be more maintainable in the future. That's my design. How can you be hypervisor agnostic? Well, we have a library for that, and it's called libvmi. libvmi is a VMI abstraction layer. It will take care for you of low-level details, like parsing the page tables or intercepting hardware events. And it will also offer you some basic introspection, like translating a kernel symbol to a virtual address. But the more important thing to remember about libvmi is that it defines you an unified, let's say, VMI interface across all hypervisors. So if you want to build a VMI application, you use VMI as the first library. So what does hypervisor support for libvmi? Xen is fully supported. At this moment, they have registers, memory, and hardware events. And KVM is on its way, thanks to Bitdefender, who have been writing awesome patches for that. So this is my final architecture. I will use Radare as the main tool for debugging, because it's really flexible and it allows me to write a debugger backend and implement my own debugger with plugins. I will write an IO plugin, which will deal with initializing libvmi and accessing the memory, and a debug plugin, which will deal with all the hardware events and the debugging events. So what's the status of this project as of today? Well, what I can do today is to intercept a process in the guest using intercepting the CR3, single-stepping the execution, and setting some memory breakpoints or software breakpoints. Also, I can load the symbols thanks to the recall profile, and I have the whole Radar2 interface on top of that. So I have graph, scripts, structures, and it's everything that Radar2 can basically provide. So now maybe let's have a demo. Yes. Okay, can see shit. So I'm starting here my debugger with Radar. This is my VM. And here I'm starting my debugger, and I would like to intercept explore.exe. As you can see, I intercepted CR3 loads until the scheduler schedules has been scheduling explore.exe. Then after that, I would like to load my symbols. So I have this command ./symbols to load the kernel symbols. And then I would like to add the breakpoints. So I have all the kernel symbols loaded into Radar2, and I would like to add a breakpoint on NT-open file, like this. And then I'm going to continue the execution. And I will trigger an NT-open file by opening explore.exe, right, like this. And as you can see, if I disassemble, we are at NT-open file, the beginning of the syscall. Also, I can single-step the execution, like this. Yes. And if I analyze this syscall, I can have the graph view of Radar2. Okay, so now we have the graph view of Radar2. I can single-step inside this graph view, and you can have the disassembly of IOP create file dynamically on the fly in the guest. But I would like to go a bit further than that. I would like to have more introspection. So I developed on top of Recall a plugin that allows me to access libvmi and access the physical memory of the guest immediately. I don't want to make memory dumps. I want to Recall to work on top of the physical memory of the guest. That's what this plugin does. So I can run pslist directly. It's going to check the physical memory. And I can also run DLL list or any recall plugin that you want. And I can use this introspection to like these addresses inside Radar2, of course. Here I'm going to take the base address of a DLL. I'm going to seek to it inside the physical memory. And if I print, I have the beginning of a PE header. So now let's skip to the next demo. You can script with RAW2. You have RAW2 pipe. First, I'm using here this my recall VMI address space to get the address of a syscall, and I added a breakpoint on top of it, and opening with RAW2 pipe a Python binding to RAW2 and continue execution. So here I have a Python script which will run the SSDT plugin with recall to extract the syscalls and all of that. And it's going to set a breakpoint on anti-open file. Everything happens in Python here, so it's a script, Python script. Okay, now I have my breakpoint which is set, and I can intercept anti-open file and print the object name associated. So now, what is the future of this project? I have some challenges, of course, because I would like not to intercept the CR3, but to attach to a thread's context and RIP. I would like to be able to break on unmapped addresses by injecting page faults. I would like to improve the introspection layer, and there are many challenges, interesting challenges to be solved on top of this. But the important thing is that my goal is to do malware analysis. And I would like to invent this kind of a framework where you have this VMI sandbox, which is dealing with extracting all the basic information that you can have, combined with this VMI debugger, which is giving you a fine-grained control over the malware execution. And you can also think of use case as fuzzing, or maybe try to debug the Windows 10 secure kernel. The important thing to remember is that RAW2 VMI is a multi-purpose, cross-platform, full system debugger. And by design, it's built for the long term, reusing a maximum of components, and also is hypervisor agnostic by design. I would like to thank all of these people for helping me, especially the people from RAW2, who helped me a lot, and Thijs for pushing me to submit, even though I had just ideas in my mind for this project. And I'm available for your questions. Thank you for your attention.
Okay, thank you. So, any questions in the room? Any questions? Anybody? Okay, as we're short for time, we'll move on. You're going to be around, so right. People have.
I'll be around. Thank you.
Oh, there's a question over there. Let's run.
Just a quick one. Can you put the GitHub address back up so that we can copy that?
Right. Thanks. Maybe I was a bit quick because of the time, but here you go. Sure.
Any more questions or requests for other slides? Am I getting in the way? Okay, well, thank you again, Mathieu.
Thank you, everyone.